Alright, welcome people. Today we're going to start with the second lesson of our financial literacy unit. So, today is all about compound interest. So, this is something more applicable in real life, more common in real life, and basically everything that we're going to talk about today is going to be about this formula and deviations of that formula. So, before we get to the examples, there are some questions in the textbook that I think it's pretty good. It's McGraw-Hill on page 502. I think they're pretty interesting. But overall, it just kind of talks about, the compounding periods and the interest rate and blah, 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 blah. Yeah, anyways. So at the end, they're going to derive this formula. And as you can see, it is an exponential function. So you're going to be growing exponentially, or you could say it geometrically. It's a geometric sequence, and yeah. So we're going to explore this a little bit, and we're going to move on. So let's start. Finding the amount compounded annually. To take a technology course, Mark borrows $3,000 at an interest rate of 4.75% per annum. Annum means year. And it's compounded annually. He plans to pay it back in 5 years. So how much will Mark owe by 5 years? So this starts, let's list out all the variables. So principal in our case, which is our starting amount. Since we already borrowed 3,000, so that is clearly our principal. Okay, now our interest rate, which is I, so it's going to be 0. It's okay. I'll write it just so you know. 4.75% divided by 100%. This cancels out, and you're gonna get 0.0475. Okay, and your n is your time. So how long are you gonna take? So you're gonna take 5 years. Okay, he's gonna take 5 years. So it is 5. Let's go ahead and plug it in. So note that in our case, they represented a as like just a letter, but in reality, we could always look at it as a at n years. Right now we have a function notation. Right, at n years we have a function notation. So let's go ahead and plug this in. So a at 5 is going to equal to 3,000 multiplied by 1.0475 to the 5th power. So you can calculate that. I will also calculate that actually. So times 3,000. So he is going to owe. Oh, why is it not working? 3,783. So I don't really care about significant digits, but I'll tell you round up to at least. You could do cents, yeah. How about 47? Sure. 40, 48, yeah, 48 cents. So this is how much he owes in total. And to calculate the interest, we basically just do 3,783.48 minus 3,000. So we're gonna go ahead and get 783.48 interest. Yep, and we're done. Let's go ahead and go to the second question. So Dama is investing $10,000 in a registered retirement savings plan, or RRSP. She is considering a 9-year plan with an interest rate of 6% per annum, compounded semi-annually, or a 9-year plan with an interest rate of 5.95 per annum, compounded monthly. Which plan should she choose, and why? So this one is basically comparing the effect of different compounding periods. I know that there is different compounding, different interests. So this leads us to our first derivation of our formula. So instead of using p plus I, we can now use something else. So, or we have to technically. So note that it's compounding 6% per annum. So how much is it compounding with respect to our compounding period? So in our case, when we have 6% per year and it's compounded semi-annually, it should be 6 divided by 2, because semi-annually means 2. So S semi-annually. So this leads us to our first derivation. It will go ahead and be P plus, oh my god, what am I doing? P bracket 1 plus I over compounding period per year. So let's do N. And now, we're going to do something else. So compound it annually. So when you have whatever exponent here, you have to make sure they have the same units. Units same. So I can't have month at the top and have year at the bottom. That's not going to work, clearly. So in our case, when we have 1 year, we actually compound it twice. So that means we do 2N. We do 2T. Right? So now we're able to figure it out. Let's go ahead and do this. So for our 9-year plan, we're going to go ahead and do compounded monthly is 12, by the way. So we're going to do A at T after 9 years of principal times 1 plus 0.03. So basically 6% divided by 2, which 6% divided by 100%, which you're going to get 0.06 first, and then you're going to divide it by the compounding period per year, which is 2 in our case. You're going to go ahead and get 0.03, and you're going to raise it up to the 2t power, which is 18. So I want you to take a moment and realize and think about it. What does 2t mean? So basically means whenever t, we're gonna input in years, right? We have 9 years. So for every year, there's gonna be 2 compounding period per year. So we have 9 times 2, so that tells us there's 18 compounding periods in 9 years. So now that we have this, we can go ahead and actually just directly do this. Know that this is 10,000. So 1 plus 0.03 to the 18th power times 10,000, it's going to go ahead and get you 17024.33. For our second one, we're going to have A at T is equal to principal times 1 plus. So instead of 6% divided by 2, we actually have to divide it by 12, because we have 12 compounding periods, right? So that is going to be an extremely small number. So I won't write it out because it's going to take a lot of digits. But you know I'll write you the exact value. So, should I? Okay, I will do 1 plus 0.0595 divided by 12 to the 12t power. Okay, that is what we have. So let's go ahead and calculate that. I will calculate that. I hope you can follow along just to see if I don't make any mistakes, because I do. Let's go ahead and raise that to the 12 power. So 12 times 9 to the 12 times 9 power times 10,000, and it's gonna go ahead and give us 17.060. All right, so we figured it out. So look at this, and you're like, okay, yeah. So she should choose the plan with 5.95% interest rate per annum. That's compounded monthly over the other plan, because it earns her just a little bit more money, just very slightly. Now, I want you to take notice that it's pretty much common sense. The more doubling periods or the more compounding periods you have, it's obviously the better. That's number one. But if these were at the same interest rate, it would have increased a little more, but it would have been a huge increase. At the end of the day, I hate it when people, they keep on telling you, oh, you need to learn how to get a better interest rate or that. I understand interest rate is very important, but I think what's more important is that you realize the capital. Because right now we have a factor of 10,000. If Dama had $1 million, then we would have noticed this change so much. So we would have earned around. Right now, we earn $36 extra with this plan. If we had $1 million, we would have been able to earn maybe like, hold on, I can't do the math right now, but a lot, like 36,000. We would have been. It's always based on your principal. So at the end of the day, if you are I guess any money is money, but if you're really trying to get on the finance side of thing, I think using leverages and getting more money in your hand is a lot better than actually trying to get a slightly higher bit of interest rate at the bank. Yeah. Um. I Hey, it's finance. Anyways, example three: find the interest rate using a graphing calculator. Yes. So this is my favorite part. I like to use Desmos because I think Desmos is it's so convenient. It's probably the go-to thing for everybody if you want a graphing calculator. Now, I know a lot of people do have the Casio, the upgraded one, which has a lot of which has a huge screen. Yeah, it has a lot of things. And some people also have TI 84, 83 as well, I'm pretty sure. But anyways, so let's go ahead and actually start doing this. So I will share my I will have to share my screen for Desmos. Desmos. Okay, here we go. Desmos. All right, so let's look at the question. Gabriella hopes the 26,000 she is investing will be worth 40,000 in 5 years to upgrade the computers. What rate of interest would she have compounded quarterly would Gabriella need to achieve this goal? So before we start, let's go ahead and actually let's do some math. Okay, let's do some math before we can do anything. So let's write everything that we have. We already know. So we want to know the a at time t. Okay, no, we already know the a of time t. It's gonna equal to 40,000, and our principal amount is 26,000. Our interest rate is what we're trying to figure out. But make sure we have to divide this by 4 because we're compounding quarterly. There's 4 quarters, by the way. And yeah, it's compounded quarterly. So so let's write this out. So a at point t would equal to p multiplied by 1 plus I over 4 to the 4t power. And obviously we have t as well. It's 5. So this goes back to solving exponential functions again. And I hate that I'm doing this mathematically, which is not fun. But it's always fun to always do the math, I guess. Alright, so we will isolate for this I. So we'll divide both sides by 26,000. So we're gonna get 20 over 13. Excuse me. 20 over 13 is equal to 1 plus I divided by 4 to the 20th power. So now you could definitely take the 20th root of this. However, not the efficient, not the greatest. So this is where we pull out our decimals. Let me just check if my decimals actually will perform this. Because I believe a lot of our decimals actually only takes variables in terms of x. Okay. Alright, yes, ours only takes in terms of x. So when you look at this, you're going to get an x-intercept. However, we don't want that. So we want to get the actual point. Minus 20 over 13 equals 0. Wow. So you're gonna notice, look, this is the same thing. So when we set it to 0, we're gonna get a definite solution for x. When we don't set it to 0, we're gonna turn the problem, as I usually say it, we're gonna turn the problem of an equation into the problem of a function. Let's go ahead and do that. So to turn into this problem of a function, we officially figured out our x value. Right, so the graphing calculator method, I understand that it's called a graphing calculator method, but really you can't do anything graphing before you can actually do the math. So after we figure out the whole of the equation and we isolate it for it, instead of taking the 20th root, which would have been a very messy, very messy process, we just looked at the graph. And fortunately, Desmos tells us that our x here is 0.087. So let's write that number down. 0.087091. Okay, let's switch back. So 0.87091. All right, so this is a rate. We have to multiply this by percent. So let's go ahead and do that. And after you're gonna do that, you're gonna get 8%. Well, to be precise, I guess 8.7%. 8.7091%. So 8.7091%. Good. So with that, we have officially figured out our interest rate. And note that because we only put x here, we define our term here as x instead of I over 4 as x. We're actually directly getting the interest rate. So when we write it, we will go ahead and conclude something like therefore we have figured out that the interest rate is 8.7091% per annum, compounded quarterly. You have to say per annum, because if you don't say per annum, it could be per month, per year, whatever. Per month, per quarter, per semi-annual, whatever. You have to state that our value here, 8.7091, it is per annum, and we have to do this, right? This is necessary. Anyways, that is it for our compound interest. Next class, we are going to get into a slightly more interesting topic of, I believe, annuities, but I could be wrong. Anyways, your homework, it is on page 507 to 510. There's some problem solving questions, and there's also some simple numeric questions that you have to do. Anyways, there's also at the end of page 511, there is an achievement check. I believe that question was pretty interesting. It makes you think a little bit, but yeah. Anyways, I believe the next lesson is where we connect compound interest and geometric sequence. All right.